Another distribution that we're going to work with is called the exponential distribution. And let's look at some characteristics of that. So an exponential distribution is tied very closely to a Poisson distributed set of data. So the previous chapter we discussed the Poisson distribution, and remember that that is a discrete type of variable, and what it looks at is a number of occurrences over a given interval. And that interval could be time or space. And what we're going to do now is turn that around, and we're going to look at its counterpart, the exponential distribution, which is continuous. What it looks at is the length of the interval that elapses between occurrences of the event. So let's go ahead and sketch this out. So on the left here we have f of x, and the formula for f of x here is equal to lambda multiplied by the constant e raised to the power of negative lambda multiplied by x. And this is only applicable for x equals to 0 because the exponential distribution cannot go below 0. So what is lambda? X is the one or two boundary values that we're solving for, just as we've done with the uniform and normal distributions in this chapter. Let's look at lambda. Let's say that if I have an average of 10 tractor trailer arrivals per hour at my terminal, that would be expressing it in the discrete or Poisson distribution. So let's turn that around. My mean is going to be the reciprocal of the lambda. The lambda is going to be the reciprocal of the mean. So in my example, the lambda is equal to 1 over the Poisson mean, and that Poisson mean is 10 trucks arriving per 1 hour. So therefore, reciprocating that gives me 1/10. So my lambda in that example would be 1/10. We'll look at a sample problem and explain some more about that. As we've been doing thus far in this chapter, what our goal is to define one or two boundary values and be able to state exactly how much area we can expect to fall between those two boundary values. So let me jot out our probability equation for the exponential distribution. So what we have here is e to the negative lambda multiplied by the a value minus e to the negative lambda multiplied by the b value. And we can write that in a couple other configurations here. So if we only are computing the area greater than one boundary value, that would take the form of e to the negative lambda multiplied by a, or if we're calculating the area less than a given x value, that would then be 1 minus e to the negative lambda multiplied by that x value. And finally, the mean of this distribution is equal to the standard deviation, and both of those are equal to 1 over lambda. So, all right, let's take a look at a sample problem. And in this problem, we're told that between 11 p.m. and midnight on Thursday night, Mystery Pizza gets an average of 4.2 telephone orders per hour. Find the following probabilities. So, expressed as a Poisson average, they receive 4.2 calls per 1 hour. So, what I'm going to do is jot that down. 4.2 calls per 1 hour tells me that I have a lambda value of lambda is 4.2. And let's proceed with part A. We want to find the probability that at least 30 minutes will elapse before the next telephone order. At least 30 minutes means that value or greater than. So the relevant formula will be this version, and at least 30 minutes corresponds to saying the probability that X will be, and here, because we have 4.2 calls per 1 hour, the unit is now hours, so 30 minutes is comparable to 0.5 hours. And using this formula is equal to negative lambda multiplied by A. A is 0.5 hours here, and that's going to give us e to the negative 4.2 times 0.5, which is e to the negative 2.1, which is equal to 0.1225. So that's our answer for part A. Part B, the keyword is less than 15 minutes. So this one's going to take the form probability that X is less than, and 15 minutes is 0.25 hours. So in this case we have the less than, so we want to use the less than version of this. 1 minus e to the negative lambda multiplied by b, and that's going to work out to 1 minus e to the negative 4.2 times 1/4, which is equal to 1 minus e to the negative 1.05, which is equal to 1 minus 0.3500, and that's going to give us an answer of 65% on part B. Part C then wants us to find the probability that between 15 and 30 minutes will elapse. So here we're going to use the full form of the equation, and it's going to say the probability that 1/4 hour is less than or equal to X, which is less than or equal to 1/2 hour. And that's going to be solved with e to the negative lambda times a minus e to the negative lambda times b. And if you look up at what we've already solved, e to the negative lambda times 0.25, we came up with here e to the negative lambda times 0.25 is equal to e to the negative 1.05, which is equal to 0.3500. And from that, we're going to subtract e to the negative lambda times 0.5, which we solved here. E to the negative lambda times 0.5 is equal to 0.1225. So we'll go ahead and do that math, and our answer for part C then is going to be that there's a 22.75% probability that between 15 and 30 minutes will elapse between telephone orders. Thanks for watching.